All right, so we're doing section 3 today, modeling with quadratic functions. But before we get going, take a look at this piece of trivia. If you plot 3 non-collinear points randomly in space, so non-collinear means they're not all in a line, and you also want them to not be vertically, so we need them to not be stacked one above the other, and they need to not all form of a line. How many parabolas can you draw through them? Think about it for a second and see if you can come up with an answer. So what do you think? You think you can draw 3? Anybody else got an idea? That was it? One person? At least one? Okay. Any other thoughts? No other thoughts? I need more than 2 people thinking. Anybody ever played Trivial Pursuit? It's a board game. You guys know what board games are? Yeah? Okay. You're bad at board games or just Trivial Pursuit? Yeah, that makes sense. I used to be bad at it too, and then I started learning more things. And now I'm not bad at it. So just draw 3 points on your page. It doesn't matter how you draw them. If I was to draw a parabola through that, how would that parabola have to go? Yeah. Is there any other way I could draw a parabola through that? Could I draw a parabola that opened up and have it go through all 3 of those points? No. Right? So that kind of rules out half the parabolas, doesn't it? I mean, there's an infinite number of parabolas I could draw. But I don't see any way I could draw an upward opening parabola that would go through all 3 of those points. It's just not possible, right? Okay. So is there any way I could draw a skinny parabola and a fat parabola that goes through all those points? No. So I'm kind of narrowing it down. The reason I asked about Trivial Pursuit is I used to play a lot of Trivial Pursuit, and my friends and I kind of came up with this theory on answering Trivial Pursuit questions. Because a lot of times Trivial Pursuit questions ask questions like, how many of some amount of things happened, right? And the answer was almost always, like if they made it multiple choice, they almost always had 0 as a choice, 1 as a choice, or some ridiculous amount as a choice, right? Or if they didn't give you multiple choice, the answer was almost always 0 or 1 or some ridiculous amount, like all of the possible options. Okay, like if it was how many states in the country allow you to, I don't know, pick something stupid, whatever it might be. The answer is going to inevitably be 0 because it's ridiculous, or 1 because it's so ridiculous that one state must allow it, like West Virginia or something, Anybody in West Virginia? I don't know. I'm sorry. I have a friend from West Virginia. We make fun of West Virginia all the time. Or all of them because it's just so absurd that it must be that all of the states allow it to happen, okay? And inevitably, that would be the case. So I'm bringing it up because that must be the case here also, okay? There's an infinite number of parabolas that we can draw. So I'm asking you to plot 3 points that are non-collinear and no 2 of which form a vertical line. How many are possible? Well, either we can't draw any parabolas ever, which is obviously not the case, or there's 1, or we're able to draw all possible parabolas through any 3 points we want, okay? Well, probably it's not going to be all of them because I just put 3 on there, and obviously I can't draw one that points up. This has to be one that's pointing down. And since I can draw one that's pointing down, it's not that I can draw 0. So what's the answer here? 1. There's exactly 1 parabola that points, that will go through all 3 of these points, all right? Now, so then, if that's the case, then where's the vertex? How am I going to draw this guy? Where's the vertex at? Is it somewhere near the top point or is it the top point? near it, I would say, because obviously it can't be either of the two lower points, right? And maybe it is the top point, but maybe more likely it's not the top point. And if you look, like it seems like we must be kind of, like the vertex has got to be kind of in this region right here, okay? Like if I just imagine the vertex being somewhere in that region right there, it kind of starts to make sense that the vertex is around there. And if I just let that point be not the vertex, then I can draw my parabola, and now that totally makes sense, okay? I just let it be, and I drew a parabola through those 3 points without forcing the vertex to be that top point, and now I have a pretty good looking parabola, okay? That's probably pretty close to what it would have to be if that was supposed to be a parabola when I drew those 3 points, okay? And you can do that all the time. I draw 3 points, doesn't really matter, okay? Oh, well, that one probably has to open which way? Oh, it probably has to open up. And I'm guessing that the vertex is going to be somewhere down here near this point, okay? And then I just draw, totally missed 2 points, but you get the idea, okay? One parabola can go through 3 points as long as they're non-collinear, they don't form a line, and no two of which are one directly above the other, because otherwise you won't have a function. This idea is what we're going to be using for the first half of this section. A parabola contains the points 0, 0, -1, -2, and 1, 6. What is the equation of the parabola in standard form? So now we're going to use these 3 points and come up with an equation for the parabola, because we know now that only one parabola exists over those 3 points. So to do this, we're going to use standard form, because it wants it in standard form. Here is standard form right here, and each of the 3 points to set up the 3 equations. So before I do that, though, let's plot these points. So we have 0, 0. We have -1, -2. Come on. And we have 1, 6. 1, and then all the way up here at 6. So let's take a look at these dots. Where, or what direction, I should say first. What direction does this parabola probably open? Probably opens up. And where is the vertex around? It's around that lowest point, probably, okay? I don't know exactly where. Is the lowest point the vertex? Definitely not necessarily. It could be that the vertex is somewhere down here, right? We don't know exactly how this parabola looks. It could do something like this, right? We just don't know, okay? Or it could be that this thing really turns around and does that, okay? We don't know. But we do know that this thing definitely opens up. Everybody sees that? Okay. So what we want to do is we want to use the standard form equation, y equals ax squared plus bx plus c. And we want to use these 3 ordered pairs that were given to come up with the equation for this parabola. And the way that we're going to do that is we're going to use these 3 ordered pairs. Each one of these ordered pairs is an x and a y. If we use those ordered pairs and plug them into the standard form equation for the x and the y, each time we do it, we're going to come up with an equation. And the equation is going to leave us with an a, a b, and a c. A, b, and c are the numbers in the standard form equation, okay? They're the coefficients that we're supposed to find. Those are 3 unknown values, okay? It seems like right now we just have a bunch of variables, but really we don't. We have 2 variables, x and y. And then we have 3 unknown values, a, b, and c. And those are the values we're supposed to find out. So what we're going to do is we're going to plug in each of these x and y values here into standard form. And what that's going to do is it's going to give us a system of 3 equations with 3 variables, and we're going to be able to solve that system using any of the methods that we have. So let me show you how this is going to work. We're going to plug in 0 for x and 0 for y using that first ordered pair. So I plug in 0 for y, so I have 0 equals, and then I plug in 0 for x, and it's kind of an unfortunate first ordered pair, right? So I plug in 0 for x, and I have a times 0 squared plus b times 0 plus c. Now that's all going to simplify down. So I have 0 equals 0 squared is 0, so I have 0a. And I know that that's just 0, but bear with me because we need that. Plus 0b plus, and there's really a 1 in front of that c, so I'm going to write it 1c. And that's my first equation, okay? Now I'm going to put a box around it so that it stands out because I want to show the work that's going on here, and normally I'm not even going to bother showing that work. But I want to show the work so that you guys can see what's going on. So now we're going to move on to the second ordered pair. The second ordered pair is -1, -2. That -1 goes with x and the -2 goes with y. So when I substitute in for x and y, I'm going to have -2 for y. So -2 equals, and then what? A times x, which is -1 squared, plus b times -1 plus c. And then we're going to simplify that. So it's going to be -2 equals what? So -1 squared is 1a, and then minus b plus 1c. I want to write that 1. Okay, now this is an equation again, so I'm going to put a box around it just so that we can see it this time. Now the other ordered pair, what am I going to write? Yes, 6 for y, so 6 equals a times 1 squared plus x is 1, so b times 1 plus c. And then simplify it, so 6 equals 1a, yep, plus 1b plus 1c. And then again, that's an equation, so I'm going to put a box around it. Now, what we have here is 3 equations with 3 unknown values. Okay, it's a system of 3 equations and 3 unknowns. So I can solve this system using what we learned in the last chapter. I have a whole bunch of methods for solving systems of equations. There's nothing that says I have to use any particular method. So which method do you want to use? Yeah, you use a matrix. That's the easiest one, right? So a matrix usually is going to require the constant coefficients to be on the right-hand side for our augmented matrix, right? So let's write the augmented matrix, but with the constants on the right-hand side. So as I set this up, I'm writing my columns for A, so 0, 1, 1. My columns for B, so 0, -1, 1. My columns for C, 1, 1, 1. And then my bar. And then the columns for the constants across the equal sign. They were on the left. Now I'm writing them on the right so that it's correct. 0, -2, and 6. Now the work that I have to show is what? Yep. RREF. And now you know why you need your calculator. What do we get? I'll go ahead and start filling in. So 2, 4, 0. Now we know that that translates to 2, 4, 0 from the last chapter, right? But that means that A is 2, B is 4, and C is 0 for us. And we want to turn that into the equation in standard form here. So our answer is going to be y equals 2x squared plus 4x. Because A is 2, B is 4, and C is 0, and we're not going to bother writing the 0. So this is our answer. Okay? We could solve it using substitution or elimination if you would rather do that. But We'd still be on like step 1 if we did it that way. So before we move on, let's take a look at what the parabola here would actually look like now that we have the equation. We have a y-intercept, of course, at 0, 0, which we already knew. And where's the vertex? How do I find the vertex? From section 2. Axis of symmetry is what? X equals? Negative b over 2a, right. So it would be negative 4 over 2 times 2, which is 4. So the axis of symmetry would be negative 1. So actually, this dot that we have here is the vertex. We didn't know it, but it actually is the vertex. And because I know that now, what can I do? We can reflect the other dots. Yeah, so I can reflect that dot, and I can reflect 1, 2, 1, 2, reflect that dot, and then I can draw in the rest of the parabola. So the directions didn't ask us to do this, but we can do it anyway. The extra practice isn't going to hurt. Okay? Now we know. It did open up, and that bottom dot actually was the vertex. So let's take a look at the second one here. What is the equation of the parabola containing these points? And I'm kind of bummed out that the point there was again 0, 0. It kind of makes the problem a little too simple, I think. But what are we going to do? Plot the points in the graph. We actually don't need to, and I'm going to skip that. Yeah, make the equations. So what am I going to write? 0 equals, and let's evaluate these guys as we go so we're not writing so much. Okay, 0a. Yep. 1c, right. That takes care of the first one. Now? Yeah, it's a y equals, so negative 2 equals. Yep. Yep. Remember, we're plugging these in for x and y, not a, b, and c. Okay, that's the common mistake that I see. So this is x squared for the first term. Okay, and the third one? Yep. Okay. Minus 1b. Yes. And again, make sure you're plugging in for x. All right. Now what? What's the matrix? 0, 1, 1 if I'm making columns. 0, 1, negative 1 for B's. 1, 1, 1 for the C's. Negative 2, negative 4 for the constants. And then, yep. Okay, and then oops. What do we get? Okay, so what's our answer? Yeah, so what's my answer then? Plus what? Plus x. Yeah, plus 0, which I don't got to bother to write. So remember what we're finding here is A, B, and C. That's A, that's B, and that's C. And A, B, and C are the numbers in the standard form equation y equals ax squared plus bx plus c. Okay? So then you plug in those numbers A, B, and C. So you have negative 3x squared plus 1x, or just x, and then plus 0, which you don't bother to write. Okay? Which way does this parabola open? Opens down. And if I were to plot those points on the graph now, I have 0, 0, I have 1, negative 2, and I have negative 1, negative 4. And if I look at those points, what is the only way that these points can form a parabola? Yep, the only way it can form is down. Okay? So it seems like we did it right. All right. So let's take a look at this problem. It says campers at an aerospace camp launch rockets. And that's like the most exciting sentence of the entire year for somebody like me. On the last day of the camp, the path of rocket 1 is modeled by this equation, where t is time in seconds and h is the distance from the ground. So make sure you understand what those variables represent. The path of rocket 2 is modeled by the graph at the right. Which rocket flew higher? What do we do? There's no need to find an equation for the graph. They're just asking for which rocket flew higher. Yeah, find the vertex, because the vertex is the maximum or minimum of something, right? So here we're looking for which one flew higher. We just need the vertex. So how am I going to find the vertex of the graph? This is not a trick question. How do I find the vertex of the graph? So just how do I find the vertex of the graph? How? How do I find the vertex of the graph? You look at it. You use your eyeballs. Okay? How do I find the vertex of the equation? Yes, negative b over 2a. And then what? Yeah, plug it back into the equation just like we were doing back in section 2. Okay? Not trick questions here. So let's find the vertex of the graph. What time does the peak height occur? 6 seconds. Right here. Okay? And what is that peak height, does it seem like? Yeah, a little under 600 feet, right? So it's kind of a guess, but we can get pretty close to what it seems like. So somebody said 575, I heard. Maybe somebody else has maybe a different idea, like what? Maybe 580. So whatever you write down, just as long as it's clearly over 550, because that is clearly over 550. We're definitely over halfway. And it's clearly under 600, okay? So whether you write 575, so the wavy equal sign means approximately. So like 575, 580, 580 what? Feet. Okay, now, when we calculate the vertex for the equation, as long as we're nowhere near what we just said, whether we're nowhere near above 580 or nowhere near below 580, we're going to be just fine, okay? We're going to have a problem, though, if we calculate the vertex for the equation and we wind up at like 572 feet, right? Because we have an approximation here and we're not sure where it actually is, right? So hopefully whatever we get out of that equation is going to be nowhere near 580 feet. Make sense? Okay. Even if the equation comes up with like 602, we're good, because the graph on this guy clearly is under 600. All right? Okay, so you said to calculate the vertex for the equation h equals, what are we doing? Yeah. Yeah. So what am I writing, though? It's not just negative b. It's an equation. It's an equation, though. X equals, but it's not x. There's no x anywhere here. T equals what? Good, negative 150. And by the way, which direction does this graph open? How do you know it opens down? But from the equation, how do I know it opens down? Yeah, we have the negative sign sitting there. Okay? Just because the variables are different doesn't change everything we know about parabolas. The squared term is negative. Therefore, this opens down. So 2 times negative 16, you guys said. Okay, now what does this become? It's positive. The negative divided by negative is positive. But what is this number? But what is that number? 4.6. We want the decimal here. This is a real world situation. So get the decimal. It's going to be easier here. Oh, it's not just 4.6?
No, it's 4.6.
875. Do you think maybe that's important? Yes, it's important. Is that it, or is there more than just... Oh, okay. All right, so let me show you guys something. I'm going to show you the calculator. Go to the calculator. And we have we know it's positive, so I'm going to ignore the negative sign. 150 divided by 2 times 16, right? But I want that to be in the denominator the whole time, so I'm using parentheses. 2 times 16, and I want the decimal, okay? So I can either press Control-Enter, which you know already, we've talked about that, or I know I want a decimal, so I'm just going to put a decimal point on there, okay? Just on any number along the way. If I hit the decimal point, the calculator will automatically give me the decimal answer, okay? Which is a really nice thing. Now, as I continue my calculations, if I use that answer, if it gave me some crazy decimal with like 12 decimal places, and I don't want to round because the rounded answer is going to give me a rounded result, which could compound the error that I'm dealing with, what I'm going to do is use the answer that the calculator gave me. Rather than some rounded answer like 4.6, I don't want to round it, okay? So now when we go to calculate, what is it that we're doing next, by the way? We're putting this back into the equation. So I need h equals, now it's negative 16 t squared, right? So it's this 4.6875 squared plus 150 times 4.6875 plus 1. And by the way, what's the plus 1? It's the y-intercept, but why is there a plus 1 there? In this, why would it start off higher? What are the units here? It's feet. Why would it start off 1 foot off the ground? Because it's a rocket on a little launch pad. Yeah. On a little pedestal. Picture like a rocket taking off that's going into actual space, right? It's going to be on a little pedestal so that it has room for the thruster engine to thrust, okay? Anyway, how am I going to enter this into my calculator? Do I got to type all that crap in? No, I don't. What I can do is I can say negative 16 times what? Answer. So if you look on your calculator above the negative sign, you see that ANS? I can type Control and then the negative sign, and it says ANS, okay? Now it will use this answer that I have sitting right there. What do I want to do that? I want to square it, so fine, hit the square. And then plus 150 times, well, I want to use that answer again, so Control ANS, and then plus 1. As long as the answer that I want it to use is the last answer that I got, this will work. Press Enter, and now I have 352.56 feet. Okay, let me get my calculator out of the way. And what do you see? It went lower. So 352.56 versus 580, okay? Not even close, right? Which one flew higher? Rocket 2 is modeled by the graph at the right. So which one flew higher? Rocket 2. And let me go back to the calculator here. If this answer, the 4.6875, was not your previous answer, so you couldn't use the ANS, what you could do is you could go up and highlight the 4.6875, press enter, and that will bring it down for you, and press enter again, and now it is the previous answer. And then you could type in that line using ANS. Okay? There's all kinds of little tricks on these calculators that I'll teach you guys along the way to help speed you up so that you're not sitting there typing in all these digits over and over and over again. Okay. So, rocket 2. That was probably the one I made. Think so? I'm lying. I never made any rockets ever. Oh, yeah? The table shows a meteorologist predicted temperatures for an October day in Sacramento, California. What is a quadratic model for the data? And then use your model to predict high temperature for the day and blah, blah, blah. Okay, fine. But what is a quadratic model for the data? This is not new. You've done linear models already. Now we're just going to do a quadratic model. Do you remember how we did linear models? Just because it was in a different chapter doesn't mean you were allowed to forget everything. No. Yeah, that's linear, but that's not the linear model. How did we do it? You did it a ton. You did it on your calculator. Use the what? Yeah, use the spreadsheet on the calculator. And then you did a what?
Graph.
What kind of graph? All right. Well, I guess I'll try to refresh your memory. We want a quadratic model. So it's going to look like standard form, y equals ax squared plus bx plus c. Okay. And we have this data sitting here. And we're going to make a spreadsheet with the data. But I don't want to use these numbers. Why? Want to use what? Want to use what? Oh, okay. So I could do that. I could say elapsed time from 8 o'clock and call 8 o'clock 0. But we're going to leave the hours, so 8 o'clock is fine. We're just going to call it 8 a.m. But I don't like the rest of it. Yeah, 24-hour format here. Because 2 p.m. looks a lot like 2 a.m. to a computer. Unless you come up with some other way to call. Yeah, exactly. We want to use 24-hour format here. So 2 p.m. is actually going to be 14. And then 4 p.m. is going to be 16. And 6 p.m. is going to be 18. Because otherwise, 6 p.m. looks a lot like 6 a.m. Okay? And we don't want that to happen when you organize your numbers from least to greatest on your scale for on your axes. Okay, so the rest of this, though, looks pretty good. So now we're going to make a quadratic model by organizing our data on our calculator. So go back to your calculator, and on the home screen, what do I need? I need the spreadsheet. So the green on the spreadsheet is the spreadsheet. And then I need to go to the top of the columns and label these guys. What am I labeling them? Time and temp is great, yep. And then remember, we're skipping over the equal sign row. We'll never type anything there. Okay, and then we're using 8 10, 12, 14, 16, and 18. And then we can just enter those temperatures as well. Okay, so now that I have that, I don't need the data anymore. Once I have this entered, what do? Back to the home screen, and then, yeah, the bar graph one, the pink one to the right of the scatter plot, this guy, data and statistics. Now I have these random dots all over the place. Now what? Click to add your variable on the axis. Which one do I want here? Yeah, the independent variable is time. As time goes on, the temperature will change. And then same thing on the y-axis. This one will be what? The temperature. So now, what kind of graph does this look like? Does this look like a line to you? No, what does it look like? Looks like a parabola. And does this make sense? As the time goes on throughout the day, does the temperature rise and then fall? Yeah, of course. So that's why we want a quadratic model for this. Okay? So, how do I put a model on here? How did I put the linear one on here? What did I do? Yeah, press menu and then analyze and then regression. Now, I usually use the linear one, but I don't want a linear one. I want a quadratic one. So I'm going with option 4, show quadratic. And there you go. Now, this one's huge, and maybe it stretches all the way across. I might have lost a digit or two. So remember that we can move that equation around so that we can see. Just in case, I will check it. So I put my, it's not going to let me. Oh, there we go. Okay, so I don't have any extra digits. It stops at 0.14. So I just write this down. But maybe it's blocked by the function, so maybe I do want to move it around just so I can see what all the letters and numbers are. So anyway, we're going to write this down. The quadratic model is y equals, and then make sure you get all the negative signs and everything. Uh-oh. Oh, just lost my equation. Try again. Okay. Okay. The calculator loves to show this plus minus, plus a negative. It's really just minus. Once we have that equation, we don't need the calculator anymore. Actually, we do, but I don't need the calculator anymore. For now. It says, use your model to predict the high temperature for the day, and at what time does this high occur? What is this asking us to find? Okay, so what is the highest temperature? Well, in the data table, we can see that the highest temperature predicted is 81 degrees, right? But according to our model, and the model is all that matters now, okay? The data gave us the model, and once we have the model is all that matters. So, what is this question asking us to find? The vertex, that's right. Okay, so if I'm asked to find the vertex, what do I have to do? How do we find a vertex of a parabola? Find the axis of symmetry and then? Okay, now we look at the B and the A, and those are just awesome looking numbers. And I'm super thrilled to have to do x equals negative b over 2a, right? Okay. Or we could probably, since we're on the calculator anyway, have the calculator do it for us, right? Does that sound better? Okay, so now I'm going to bring my calculator back. But the bummer is the calculator will not do what we want it to do from this screen, okay? What we need to do is go back to the home screen and bring in a graph. So I'm going over to the graph icon. It's the one that looks like a parabola already, which is convenient. So I bring up the graph icon, and we're going to type in this equation, okay? So just type in that equation. And we press enter. And when we do, I see a line. How come? It's supposed to be a parabola. Yeah, good. It's the window here is like super zoomed in on a portion of the parabola. So what do I need to do? Okay, yeah, we're going to be good PC users, not Mac users. And we're going to go to Window Zoom and Window Settings. And we're going to change this thing so we can actually see what we want to see. Now, which way does this parabola open again? And how would I know which settings I want? Actually, I'm going to hit cancel. How would I know very easily which settings would be best? Going what? What do you mean? Yeah, good. So if I go back to the screen that had the model on it, so by doing that, I can press Control left, or I can move my mouse up to the tab 1.2. This has scales on it. And all I need to do is be able to see my vertex, right? And then the calculator will be able to calculate my vertex for me. And by the way, notice that the model here does not come up and touch that highest dot. It's actually pretty far below that highest dot, and that's fine. The model is going to do the best it can and come as close as possible to all the points, but it's not necessarily going to touch any of the points, and that's okay. We remember that from when we were learning about linear models as well. Okay, so we see a scale here. It looks like it gets all the way up to 78, so maybe if I go a little higher than that, like what? 80, great. So that's my Y maximum, and then for the X maximum, I probably need to get all the way over to what? So I see 18 for sure. So just to make life easy, maybe 20, right? So now I can go back to tab 1.3, and I can go to Menu and Window Zoom and Window Settings, and my X minimum can just be 0. My X maximum can be 18 or 20. And then my Y minimum can be, oh, I hate this. Oh, there we go. Hey, that's nice. Y minimum can be 0, and Y maximum, I didn't know it would do that, would be, what did we say? 80. Good. And now I can hit OK, and I can see my parabola. Okay? It's way up at the top there, and I don't like that very much. Usually I like to see a little bit more white space above, but hopefully this will be okay. Now the nice thing is the calculator will calculate what I want it to do. So how do I do that? Menu, Analyze Graph, and what of these options am I going to probably pick? Maximum, because it opens down and I want it to give me a maximum. So now we've seen the lower bound and the upper bound situation before. Lower bound means I just go to the left side of what it is that I'm trying to find, which is my vertex, and then I click, And when I click, the lower bound thing changes to upper bound. And then all I do is I slide across until I have my vertex. And when I do, it will give me the ordered pair and show me the word maximum. And then I click again in the center of the mouse pad, and I have my maximum. Now my settings are set to give me the most decimal places I can possibly get. Your calculators are not. You probably only have like 1 or 2 decimal places, right? 1 decimal place? Okay, so what did your calculators tell you? The ordered pair 15.7 and 79.4. Right. So now the question is, what are these numbers? What is the 15.7? It's the x coordinate, but what does x represent for us in this problem? It's time. So 15.7 hours and 79.4 what? Degrees Fahrenheit. Now 15.7 hours is what time? 3 something, right? So 79.4 degrees Fahrenheit at 3. Now, do you remember what we did when we were talking about the populations of Detroit and San Diego and things like that? So we go back to the home screen. We can go to the calculator. 0.7 of an hour. What do we do? 60 times 0.7. 42. So 3:42 p.m., 79.4 degrees is your high temperature. Okay? That's it. Let's see. What's the next one? It's the same problem, basically. And I think we can probably, I mean, it's basically the exact same problem. So we can probably skip this. You guys agree with that? I mean, it's just doing the same thing over again. So let's put an X here, just to remind us that we skipped it. And we'll call that section good.